Up to this point, we considered vectors in a state space. Vectors represent qubits, which we use to store quantum data. But for real computations, we need more than just to store something. We have to be able to modify it, usually according to some plan, called an algorithm. So we need an instrument which is able to modify vectors, or from physical point of view, which modifies the physical state of a system. In general, an operator is a thing which maps vectors to vectors. Let H be some Hilbert space. Then an operator A is called a linear operator on H if for any two vectors x and y and two scalars alpha and beta, the action of A on alpha x plus beta y equals to alpha ax plus beta ay. We already know that in quantum computing we deal with qubits, which means that the state spaces we usually consider are finite-dimensional. For a finite-dimensional vector space H, a linear operator A in that space can be represented as a square matrix. The action of operator A on vector x, in this case, is a simple matrix multiplication. To obtain the resultant vector, we multiply the operator matrix by the vector column, and we obtain another vector column. Each component of this resulting column is obtained by matrix multiplication of the corresponding row of the matrix A and the column x. So we can consider an operator as an ordered set of linear functionals. Each row of the matrix represents some linear functional, and the operator's action on a vector is a vector which components are the results of the corresponding linear functionals applied to this vector. Good. Now let's consider some linear operator A with its matrix representation. And we are going to apply this operator to the first basis vector of the orthonormal basis, that with single 1 as the first component and with all other components being zeros. What are we going to obtain as the result of this operation? Well, it's pretty obvious that we obtain the vector which is identical to the first column of the matrix A. And with any other vector of this kind, with single 1 on a place k, the action of A on this vector will result in the kth column of the matrix. This gives us a very simple method for obtaining the matrix representation of any linear operator. If we know how an operator acts on this particular basis, then we can construct the matrix column by column by sequentially applying it to these basis vectors. This method is worth to remember, especially if you want to take my another course, the Introduction to Quantum Computing. There are going to be exercises where you will have to construct the matrix of an operator according to some circuit scheme. So if you understand how the scheme transforms basis vectors, then you should be able to construct the operator that represents column by column. Linear operators in a Hilbert space form a special structure that mathematicians call algebra. This means two things. First, the linear operators acting in a linear vector space also form a vector space. And second, the operators can be multiplied. And the result of this multiplication is a linear operator in the same space. Let's consider this in more detail. We start with the notion of a linear vector space. For linear operators to form a vector space, we must properly define two operations: multiplication by scalar and addition. Here on this slide you can see the definition of these two operations. The capital letters denote operators, while little letters denote scalars. For an operator A and a number lambda, the action of operator lambda A is the action of A and then multiplication by lambda. And for the sum of two linear operators, A and B, it is also a linear operator, A plus B. It acts on any vector x as if we apply separately A and B to it, and then add up the results. In the matrix representation, the matrix of A plus B is a matrix, each component of which is obtained by addition of the corresponding components of A and B. And the matrix lambda A is the matrix of operator A, each component of which is multiplied by lambda. And since we now have this addition and multiplication by scalar properly defined, we also must have the special element in this vector space, which is neutral with respect to addition, the zero element, which is represented by the matrix consisting of all zeros. For any operator A, we can also define the operator minus A. The addition of A and minus A gives us this zero operator. This allows us to conclude that the matrix of minus A consists of the same elements as the matrix of A, but with the minus sign. It is easy to show that this sum operation is commutative and associative, and it is distributive with respect to multiplication by a scalar. So the linear operators form a linear vector space, indeed. Now, what about their multiplication? The product of two operators, A and B, is defined like this. When we apply the operator AB to some vector x, we first apply B and then A to the result of the action of B. The operation defined like this has some very useful properties. It is associative and distributive with respect to addition, but it is very important to know and remember that in general, linear operators do not commute. It means that the order of the application matters in most of the cases. In general, the operator AB is not equal to BA. However, for some pairs of operators, it is not true. To distinguish these two situations, we have a very simple instrument called commutator. The commutator of two operators, A and B, is itself an operator, defined like this. Whenever you see in a textbook on quantum mechanics this notation, two operators placed in these square brackets, you must understand that this is just AB minus BA. If it happens that AB equals to BA, then this expression is just a zero operator. And it means that operators A and B commute. And from the physical point of view, these operators may represent observables. We'll talk about this later. And it is very important to know whether some pair of observables commute or not. So this commutator is a simple yet very powerful and useful thing.